aja. Ya udah sambil kita menunggu ya. Baik, pada hari ini kita alhamdulillah ya kedatangan 2 tamu dari UTM Malaysia. Nanti saya akan memperkenalkan, kedua tamu kita sudah hadir di depan. Namun sebelumnya sebagai lazimnya kita memperkenalkan salah satu research group ya dari yang ada di Departemen Teknik Elektro. Jadi untuk hari ini karena saya dari research group Antenna Propagation and Microwave Research Group. Jadi di sini memang kita lihat yang kita ambil hanya A, M, R dan G ya. Karena antenna propagation itu kan satu society ya, microwave juga satu society lagi yang ada di IEEE. Baik. Terima kasih. Pointernya ini ya. Belum mau. Belum mau. Belum mau. Belum mau ya. Ya udah, berarti masih harus manual. Baik, pada kesempatan hari ini yang hadir offline ada dan yang online sudah cukup banyak ya. Berapa sudah yang online? 30 atau berapa? Udah 49 ya, hampir 50. Baik, ini yang menarik juga grup leadersnya 2. Biasanya kan hanya 1. Ya, jadinya kita ada 2. Ya, jadi Prof Eko mungkin sudah kenal ya kemarin, terus saya sendiri Yuli ya, jadi saya Prof Yuli. Kenapa berdua? Karena Prof Eko bilang perlu regenerasi, beliau mengatakan sudah mau pensiun, jadinya sudah mulai diberikan ke saya gitu kira-kira, tapi masih berdua ya. Prof Eko inilah yang melahirkan AMRG, jadi saya termasuk anggota pertama lah ya di AMRG. Berikutnya, baik, ini sedikit sejarah AMRG ya, history. Jadi lahir AMRG sudah cukup lama ya, 1997 ya. Kemudian kita banyak perkembangan. Pertama kali anechoic chamber itu di tahun 2000. Ya, anechoic chamber. Tapi kemudian direhab, direnovasi lagi. Yang terakhir 2017 apa 2018 kita renovasi yang sudah bisa dilihat ya kemarin. Kemudian VNA baru ini kita berhasil dapat di 2021. Jadi kita terus-menerus mendapatkan pendanaan, kita beli lagi alat baru, kabel baru dan seterusnya. Nah, yang tercanggih VNA baru ini yang sampai 40 GHz ini di tahun 2021. Baik, berikutnya ini sedikit research roadmap karena kami terdiri dari banyak anggota, jadi nggak mungkin semuanya kami masukkan. Namun di sini yang kami selalu melihat ya, kami meneliti ada di paling ujung ini, kita masih tertarik ya dengan antena dan sirkuit RF ya pada berbagai aplikasi. Kemudian kita juga perbaikan kinerja antena atau performance-nya ya, enhancement untuk berbagai macam antena, terutama microstrip. Kita bisa menggunakan EBG atau DGS, kemudian metamaterial. Terus juga teknik pengukuran antena pernah kita juga lakukan ya, bagaimana dari near field kita translate ke far field ya. Kemudian ada computational electromagnetic yang sekarang ada yang juga melakukan riset terkait machine learning untuk desain antena. Kemudian nano antena karena kita sudah ada juga yang bekerja di terahertz. Kemudian biomedical dan integrated miniaturized antenna ya. Jadi seperti itu yang kami sudah lakukan ya, dan terus sesuaikan juga dengan kondisi. Jadi kami juga melakukan IoT juga, research IoT juga ya untuk berbagai aplikasi juga. Baik, next. Baik, ini dia lecture members yang di AMRG. Kemarin mungkin juga sudah melihat Dr. Catur Apriyono. Kemudian Dr. Basari sekarang sudah menjadi Kaprodi dari Biomedik. Ya, jadi kita ada Kaprodi 3 di bawah Elektro, Biomedik, Teknik Komputer dan Elektro sendiri. Ya. Berikutnya di sini ada anggota kehormatan, ya, karena mereka juga sekarang sudah punya research group sendiri, ya. Tapi dulu mereka pernah bergabung juga di MRG, ada Prof. Gunawan Wisono dan Profesor Muhammad Asfial. Berikutnya, nah ini dia ongoing students. Di sini udah kelihatan 2, yang S3 ada 4 ya, yang lagi progres. Kemudian di sini suasana di lantai 2 nanti mungkin kita bawa ya, di bawah sini lantai 2. Baik, next. Ini dia alumni dari S3 MRG, sudah ada yang menjadi profesor juga, jadi kita juga senang gitu ya. Saya termasuk yang jadi profesor dari bimbingan Prof Eko, tapi dari bimbingan saya sendiri juga sudah ada yang jadi profesor. Ya, jadi itu kesenangan bagi kami sendiri. Ada yang malah sudah menjadi rektor, ya, wakil rektor, dekan, ya. Jadi alhamdulillah posisinya sudah bagus juga di tempat mereka bekerja. Berikutnya, ya, pendanaan riset kalau dari kami semua ya itu sudah lebih dari 60 hibah, publikasi juga sudah lebih dari 200 karena memang kami tidak bisa hitung ya karena anggota kami cukup besar. Ini perkiraan saja. Nah, yang ini dia lab ya yang kita lihat di lantai 4 dan ini adalah beberapa paten-paten yang kami coba juga daftarkan. Ada yang sudah kami peroleh juga berupa hak kekayaan intelektual, hak cipta. Kemudian tentu kami juga publikasi alhamdulillah sudah semakin banyak ya yang tembus Q1 paper like IEEE ya dan seterusnya. Baik, berikutnya. Silakan, ini sedikit video tentang MRG. Suaranya kok tidak ada? Baik. Tadi pas tadi coba bisa ya. Lagi ngambek lagi nih. Jadi tadi habis waktu sedikit karena coba audionya, tadi bisa, sekarang hilang lagi ya. Tapi kalau nggak bisa juga ya nanti saya yang jelaskan. Oke, baik. Ini salah satu contoh antena array ya yang kita buat menjadi bagian dari VTS, radar VTS ya. Jadi radar yang digunakan untuk bukan di bandara tapi di laut. Jadi untuk pelabuhan di laut itu tadi contohnya hasil radar ditangkap. Jadi kalau ada kapal keluar masuk bisa ditangkap oleh radar, antena radar ini ya. Oke, dan kemudian tentu ini kita bisa lakukan karena kita punya fasilitas riset. Contohnya ini adalah anechoic chamber. Udah mulai masuk ya, tapi masih bergema. Ya udah, biar saya saja yang jelaskan. Jadi ini VNA tadi ya yang kita punya bisa otomatis ya memperoleh, kita putar turntable-nya bisa dapat pola radiasinya dari hasil putarannya. Jadi kita bisa dapat, ini kan berputar nih turntable-nya, kita bisa dapat pola radiasi, gain, jadi parameter S21 selain tentunya parameter S11 dari antena. Dan kalau sudah di dalam ruangan ini ruangan yang kedap ya, jadi tidak ada gelombang elektromagnetik yang bisa masuk maupun keluar. Ini contohnya dia masuk dengan handphone, ditulis tidak ada sinyal, jadi masuk ke dalam sana ya tidak ada sinyal. Jadi jangan sampai terkunci ya di dalam ruangan anti gema tersebut, nanti nggak bisa minta tolong ya karena nggak ada sinyal teleponnya. Baik, next slide, ini terakhir. Sudah? Oh, ada terakhir di video ini terlihat kami ya, tim MRG, tapi tentu sudah belum yang terupdate lagi. Kita terus menerus soalnya ada yang keluar masuk. Baik, demikian dari saya terkait MRG. Semoga yang hadir maupun profesor bisa tahu ini adalah salah satu research group yang ada di elektro ya. Dan secara rutin FMF ini memang memperkenalkan, ya, setiap pekan kita bergantian, ya. Pekan ini dari riset grup saya, nanti pekan depan dari riset grup yang lain, ya. Jadi mahasiswanya bisa mahasiswa dari riset grup itu yang akan menyampaikan, ya, hasil perkembangan risetnya kepada koleganya yang S3 di sini pada umumnya, atau tadi ada undangan misalnya seperti ini, ya. Jadi kita juga bisa membawa kolega kita dari kampus lain, atau kita bisa bawa dari industri untuk hadir mengisi acara FMF ini. Baik, itu sedikit perkenalan dari riset group yang ada di sini, salah satunya yaitu MRG, tempat saya berada. Selanjutnya saya memperkenalkan pembicara, ya. Pembicara pertama, siapa duluan? Prof dulu. Baik. Baik, pembicara pertama ini Profesor Insinyur. Jadi sama ya. Kami juga insinyur juga ya, profesi ya. Dr. Sharul Kamal Abdul Rahim. Nah, nanti bagi yang hadir, mereka ini karena dari Malaysia bisa campur ya. Boleh bahasa Inggris bertanya, boleh bahasa Indonesia. Ya, nanti kalau kurang jelas saya bisa translate. Tapi kalau mau langsung bahasa Inggris, oke, ya, karena biar mereka langsung paham. Karena ada kemungkinan bahasa kita enggak persis sama artinya ya. Tadi bisa nangkep, tadi bisa mengerti ya, cukuplah ya. Baik, Profesor Sharul Kamal obtained his first degree in electrical engineering from the University of Tennessee, USA in 1996. Building on this foundation, he earned his M.Sc or Master in Science, yeah, in Communication Engineering from Universiti Teknologi Malaysia, and later pursued a PhD in Wireless Communication System at the University of Birmingham, UK, yeah, completing his studies in 2007. Jadi itu latar belakang pendidikan beliau ya. UTM-nya di S2 ya, S1, S3-nya di luar negeri. Baik. Nah, kemarin sudah dibacakan banyak juga CV-nya, jadi saya langsung yang terakhir ya. His involvement in the Institution of Engineers Malaysia Southern Branch includes roles as Vice Chairman from 2016 until 2017 and Executive Committee Member from 2012 until 2016. Currently, he serves as the Chairman of Technical Committee under Standard Malaysia. Yeah, he is also an esteemed member of professional organization, yes, such as senior member of IEEE, and of course involved in Malaysia's section, members of Institution of Engineers Malaysia, member of the Institute of Electronics, Information and Communication Engineers, yeah, and that's from Japan, right? And a member of the Etakapanu chapter. This is new. So, his multifaceted contributions highlight his commitment to advancing both academic and professional domains in the field of electrical engineering and wireless communication. So, without further ado, the time is yours, Professor, around 40 minutes, yeah? Because after that, Dr. Norhudah, and then also discussion.
Okay, Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin, wassalatu wassalamu asyrafil anbiya'i wal mursalin wa ala alihi washabihi ajmain. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Terima kasih ya, kepada pengerusi majlis Prof Fitri ya. Terutamanya bersyukur saya kepada Allah SWT ya, kerana dengan limpah dan kurnianya dapat saya bersama-sama dengan tuan-tuan dan puan-puan pada sesi pada pagi ini. Actually, it is actually an honor for me to be here together with my friend Dr. Huda. Yeah. And terlebih dahulu ya, saya rasa kita nampak ya, terlalu banyak achievement ya, yang diterima ataupun dah dibuat oleh Prof Fitri, Prof Eko dan juga tim beliau. Jadi saya rasa agak kekok lah saya nak mengajar Prof yang hebat ya. Tapi walau bagaimanapun berilah peluang pada kami ya untuk share sedikit ya some informations tentang apa yang kami buat di UTM Malaysia ya. Dan okay, untuk makluman tuan-tuan dan puan-puan ya, ibu-ibu dan bapa semua, tujuan kami ke sini adalah kerana tujuan ini, iaitu matching grant ya. Untuk makluman semua, sebenarnya kami ada satu matching grant ya, bermula pada tahun lepas ya, antara UI, Universiti of Indonesia dan juga UTM, Universiti Teknologi Malaysia ya. Dan di sini kita ada students dari kedua-dua negara, daripada UTM dan UI. Dan kami ada beberapa output yang kami perlu buat ya. Dan pada tahun lepas Prof Yuli ada ke UTM ya. Kami menjemput beliau ya, dan alhamdulillah pada tahun ini ya, kami berdua dapat ke sini, dan insya-Allah di masa akan datang kami berharap ya, lebih ramai lagi daripada UI boleh ke UTM ya, dan lebih ramai daripada kami juga boleh ke sini lah ya, insya-Allah. Okay, so ini adalah merupakan team members ya, antara kedua-dua grup ya, dan ini merupakan title of the proposals ya, which is related to metamaterial as well as the MIMO antenna ya. Okay, so please allow me to speak in English ya. Maybe saya bercampur-campur sikit ya. Alright. So basically this is actually the content of my presentation today. Yeah, so it start with introductions, yeah, about UTM. Yeah, kemungkinan ibu dan bapa-bapa ada pernah ke UTM, maybe belum. Yeah, so saya akan explain sedikit tentang UTM tersebut. Yeah, seterusnya tentang WCC. Di sini ada antenna AM research group AMRG. Yeah. So di UTM kami ada WCC, Wireless Communication Center. Ya, so apa itu WCC? Nanti saya akan explainkan juga ya. Seterusnya saya akan pergi kepada evolutions of wireless mobile communications. Ya, seterus itu kepada antenna and beamforming network. Ya, dan seterusnya adalah case study. Ya, untuk makluman ibu-ibu dan bapa-bapa semua. Ya, apabila kita buat research ya, in some cases kita juga mau pergi atau menggunakan untuk industri ya. So kami di-approach oleh industri untuk kami buat satu sistem ya, on the monitoring system di Johor ya. And di situ juga kami ada satu grant daripada Japan, dinamakan sebagai Asian Evo Grant. So saya akan explain apakah Asian Evo Grant, dan saya berharap selepas ini kemungkinan daripada UI juga ya, boleh bermohon dan menjadi head of the group ya, untuk grant ini. Dan lepas tu maybe mungkin boleh invite kami pula lah sebagai members ya, of the team ya. Dan akhirnya adalah conclusion. Okay, so please allow me to speak in English ya. Alright. Okay, so basically when we are talking about UTM, yeah, so basically UTM is one of the public institute in Malaysia. So in total we have about 20 public institute in Malaysia, and UTM is one of them. And UTM is actually one of the, I would say, one of the biggest, yeah, if not the biggest, maybe one of the biggest institute in Malaysia and one of the oldest in Malaysia. So basically we started as the technical school in Kuala Lumpur in 1904, 1904, ya. Seterusnya pada tahun 1946, ya. Alright, we have been upgraded to become the technical college, ya. In 1972, we have been upgraded into the National Institute of Technology, ya. So the UTM itself just started in 1975. Yeah, so they say we are talking about UTM itself. UTM is, I would say, is much more younger than UI. Yeah, I would say UI having started like long time earlier than us. Yeah, so that's why we think that UI is actually a very good or a very suitable partners for us. So that's why we are here. Hopefully we can explore and innovate more opportunities. Yeah. All right, so this is actually how UTM looks like. So in general, we have 3 different, what do you call that, campuses. So the first one is actually in UTM Johor Bahru. Yeah. So this will be our main campus, the new campus, because we have just shift in from Kuala Lumpur to Johor Bahru in 1980 something, 85 or 86. Yeah. And the area of UTM Johor Bahru is around 1,148 hectares. I'm not so sure about UI, but 300 hectares. Yeah, all right. Still very big, yeah. Okay, but in general, in UTM JB, I would say only 50% has been developed. The rest is still paru-paru dunia. Yeah, but still, you know, a lot of trees. Yeah. And the one which is a bit slightly smaller is located in Kuala Lumpur. Yeah, we call it as UTM International Campus. And the area is only 35 hectares. Yeah, but the good things about UTM Kuala Lumpur, yeah, is actually because of the location. Our location is very close to KLCC. Ibu-ibu dan bapa-bapa semua pernah KLCC tak? The Twin Tower, Petronas Twin Tower. So from our campus to Petronas Twin Tower is only about 1 kilometer away. Meanings, I think we can walk to KLCC. Yeah, so sangat-sangat hampir. Jadi itu yang kami amat berharap, ya, in the future ibu-ibu bapa semua boleh datang ke kampus kami di Kuala Lumpur ataupun Johor Bahru. Okay, in terms of the world ranking, QS world ranking, basically yesterday I talked to Prof. Fitri. I think one of the KPI of the university is actually about the ranking as well. So we actually also included in this scenario. Yeah. So basically, when we're talking about UTM world ranking, QS ranking, basically we have, alhamdulillah, we actually have quite a reasonable good ranking. Yeah. So our ranking in 2024 is 188, yeah, and rank in Asia is number 39 in year 2022, and in terms of the world ranking by subjects, I think in general we have quite a good positions, yeah, for engineering and for other faculties as well. Okay, so this is actually an illustrations of Malaysia. So basically in general, Malaysia is divided into 2. Peninsula Malaysia, yeah. So this is the peninsula of Malaysia, Sabah and Sarawak. So from here you can see that, yeah. So this is actually the location of UTM Johor Bahru, and this is the location of UTM Kuala Lumpur, yeah. So for UTM Johor Bahru, this is the main campus. So if they say you can see this small red area, this is actually we call it as Singapore ataupun Singapura, yeah. So the distance from Singapore to us is only about 25 kilometers away. So basically, if they say, if I go to the city center, yeah, I drive for about 20 kilometers, then I went to this place. Basically, we can see Singapore, or even we can swim to Singapore. So it shows how close it is. Actually, very, very close. Yeah. Even we can walk. Yeah, we can walk. Yeah, I think very close by. So that's why I think we really encourage everyone to come over. Okay, just now for Prof. Fitri did mention about her group. Yeah? So basically we also have some historical about WCC itself. So basically in general we started in 1989 as the research laboratory. So this is where we started. Yeah, I think about similar time, yeah, with Prof. Fitri groups. Yeah? And in 2003 basically we have been upgraded to become the COE, Center of Excellence, by Ministry of Education Malaysia. Kalau di sini saya katakan Ministry Pengajian Tinggi. Okay. Okay. So Ministry of Education Malaysia. Yeah. Okay. And I think, and later on, yeah, in 2013, we have become one of the, they call it as a high-profile research center in UTM. I think similar like what you have over here. Yeah, and in 2014, yeah, we have been awarded as HICoE, High Center of Excellence, by the Ministry of Higher Education of Malaysia. So basically, the award comes with some rewards. Yeah? So basically, we have been given some allocation of money, yeah, in order to upgrade our facilities, as well as opportunities for us to collaborate with outsiders, yeah, industries, as well as from the higher education. Yeah. And later on, yeah, I think we also have been given another chance. They call it as a HICoE second phase because of our performance. So we have been given the second chance, yeah, to extend, yeah, I would say our title, for the HICoE for second term until 2021, yeah. And we also have been chosen to become ITU COE. And so basically, we had conducted a lot of courses, yeah, and everyone also actually welcome to join the courses. So basically, around the way, we have collaborated with many industries, yeah, with many universities, yeah, and one of the industries that we would like to highlight is Ericsson. Yeah, Ericsson is a company from Sweden. So basically, we have been collaborated with Ericsson for more than 20 years. Yeah. And Ericsson is actually the only company that has been given the, I would say, contract by the government of Malaysia to install 5G in Malaysia. So this is actually due to our collaboration with Ericsson. So basically, this is the benefit that have been awarded to Ericsson. Yeah. And in addition to that, we also have collaborated with many international universities. Yeah. For example, we also have collaborated with University of Surrey, which is in London. Yeah. And some other universities as well, which, you know, I think we have a lot of lists. And we hope UI, or we can see UI is already part of our partners, yeah, for these collaborations. Okay. Okay, next I think I would like to go to evolutions of wireless mobile communications. Okay, so ladies and gentlemen, yeah, ibu-ibu dan bapa-bapa semua, yeah, basically when we are talking about mobile phone, yeah, mobile phone I would say play a very crucial role to all of us, yeah. So setiap pagi, kalau ibu-ibu dan bapa-bapa semua perasan, ya, apabila kita bangun pagi, ya, dan kita akan tengok apa, ya, kadang kita akan tengok kita punya mobile phone. Ya, kita tengok WhatsApp, berapa WhatsApp masuk, kita tengok TikTok, ya, kita tengok email. So it shows that, yeah, mobile phone or smartphone play a very crucial role to our daily life, yeah. Nevertheless, the first mobile phone was started or developed in US in 1945. So basically, in this first mobile phone system, you can see that they have a very tall tower with a very high transmitted of energy. Meaning power transfer is actually very, very high. Why? The reason is because, you know what, the system need to cover a very wide area because that is the only radio base station which is available in that particular of time. So whoever within the area will be able to communicate. But those who are actually outside the, I would say the cell, will not be able to communicate. So that's why they have to make it to be very, very tall and transmit a very high power to cover a lot, I would say, a wide area. Yeah. So this is actually an illustration of first mobile radio. So you can see, ya, bapa-bapa dan ibu boleh lihat, ya. Di sini kita ada kereta, ya, ataupun kereta dalam bahasa Malaysia adalah mobil, ya, mobil, okay, mobil, ya, mobil, ya. Yeah, inside the vehicle itself, yeah, we have the radio unit, yeah, and the radio unit is actually the one that communicate to the radio base stations. So whenever the vehicle is actually moving, then this is where we have the first mobile radio. Okay. Okay. Then due to some problem of congestion as well as spectrum issue, basically the cellular concept has been introduced. Yeah. So what is actually the cellular concept? Yeah, so basically cellular concept is actually a concept where the area has been divided into small cells, and each of the cells, yeah, have their own radio base stations. So whenever we are actually in one of the cell, like over here, and let's say we are here in this day one, yeah, we are here, and of course there will be like one radio base station which is connected to us. So whenever we want to communicate, we will be able to communicate either uplink or downlink from here, and so that we can communicate to other people, either within this cell or outside the cell, right? But in this concept also, yeah, but the problem is actually as a human being, we are not static. We're actually moving from one place to another. For example, they say, maybe now you are here, but maybe in 2 hours later, you might be going to Jakarta Central. So you will be moving from one place to another. So there is actually a concept where they call it as a hand-off, yeah, where, yeah, the control of the radio of the cell ataupun of the users itself will be hand over to the adjacent cell. Yeah, so this is actually what we call as the handover. Yeah. So in general, we can see that, yeah, with this, yeah, it can improve in terms of spectrum efficiency, yeah, as well as can also solve problem of the congestions. Yeah. And this is actually an evolution of wireless mobile communication. So basically, we have to know when it is actually started. Yeah. So basically, this modern mobile communication started in 1980s as an analog devices, yeah, or analog system. 10 years later, in year 1990, 2G was introduced. So basically, it is actually digital-based communication ataupun digital-based system, yeah. And 10 years later, in year 2000, 3G was introduced. So basically, for 3G, the data can go up to 2 megabit per second, yeah. And this is where internet has been introduced, yeah. And later on, in year 2010, 4G was introduced, and this is where I think in Indonesia we use a lot of 4G, right? Yeah, it's introduced in 2010. So this is where LTE was introduced, yeah. And the data rate can go up to 1 gigabit per second, yeah. Then I think 5G was introduced in 2020, yeah. So basically 4G, it is actually 10 times faster than 4G, yeah. And for 6G, yeah, so this is something which is in 2030, right? All right, so for 6G, it will be introduced in 2030. So hopefully we actually sampai ke 2030, all right? And for 6G, yeah, so in terms of the speed, it is 10 times faster than 5G itself. It can go up to 100 gigabit per second with very small latency, which is in terms of microseconds in terms of the latency. Yeah. So just now I did mention about the evolutions of mobile communication which occur every 10 years. Yeah, so start from 1G until up to 5G, 6G, and etc. But in terms of the creations for market, basically it occurs every 20 years. Yeah. So basically the first wave of this creating new values for the market, yeah, it occurred from 1980s to 1990. So this is where the concept is actually mobile phone for everyone. And then now you can see nowadays the objective has been achieved, yeah, where everyone, yeah, including our grandparents, are having their own mobile phone. Yeah, so the objective has been achieved. So the second objective is actually they call it a second wave, yeah, occurred between 2000 to 2010. Yeah, so basically the objective is actually a variety of apps and video. So now you can see nowadays, yeah, you can see a lot of apps, yeah, a lot of videos, yeah, TikTok, YouTube, yeah, IG, yeah, Facebook, etc. has been introduced, and this is where, yeah, they have achieved this kind of objective. Yeah, and the third one, which is occurring right now, yeah, they call it as the third wave. Yeah, yeah, and the concentration is actually on the society as well on human-centric. Yeah, so this is actually occurring right now. And it is very interesting for us to see what will happen during this particular time. So I did mention about 6G. Of course, I will not want to call that explain very details about 6G, but it is good for us to have some understanding about the 6G, the mission in 2030. So basically for 6G, actually we are talking about future wireless access. Yeah. So we are talking about 5 different domains. Yeah. So currently, when we actually right now we are talking only about terrestrials. Yeah, terrestrial domain. Yeah. You say you can see from here. We are only talking about terrestrial domain. We are talking about vehicle-to-vehicle communications, communication from base station to us, and etc. But for future wireless access, we are talking about 5 domains, which include space domain. Okay, we are talking about air domain. So this is where UAV, HAPS, yeah, what do you call that, will be used, yeah, extensively. Yeah, and then in addition to that, we are also talking about ships as well as underwater domain. Yeah, so this is something that will be extensively be utilized and will be used for the future applications. Yeah. So basically, when we are talking about future wireless access, we are talking about unlimited access of information and data sharing. Meaning, not only those actually covered by the base stations or by the self, but we are talking about anywhere, anytime, for anyone and anything. So in this case, yeah, we are talking not only like what we have right now, which is here, but we are also talking about those living in desert area as well as those who are actually traveling on the open sea. So they will be able to have, yeah, this kind of the communications. Yeah. Okay, so as we know, okay, for 5G we have three pillars, yeah, EM, BB, URLCC, as well as MMTC, yeah. But for 6G, we are talking about 6 requirements, which is very important. The first one is actually about extreme high data rate. Yeah, so we are talking about data rate which is more than 100 gigabit per second. Yeah, and in terms of the coverage extension, so we are talking about global coverage everywhere. So not only on the terrestrial, we are also talking about, you know what, desert, sea, and etc. Yeah. And we are also talking about devices free from battery charging, yeah, without battery, yeah. And we are also talking about massive connected devices. So we are talking about 10 mega devices, yeah, per kilometer square. So as you can see nowadays, yeah, people, yeah, they are using a lot of wireless devices. Yeah, maybe some of you might have 2 mobile phones, and like me, I have only 1. Maybe you also have the smartwatch. Yeah, maybe Bluetooth and etc. So this is actually like you can see like nowadays, easily, yeah, 1 people have 2, 3, or 4 devices attached to themselves. Yeah. So we are also talking about reliability. Yeah, talking about quality of services, which is up to 99.99999% in terms of the reliability. Yeah. And we are also talking about end-to-end, very low latency, which is in terms of microseconds. Yeah? So this is actually the requirement for the future wireless technology. Yeah? All right, next one, I'm going to go to antenna and beamforming network. Yeah. All right. So basically, these are actually research team in our center. So basically, in our center itself, we have 4 different area. Yeah. The first one is on the propagation and RF microwave. Second one is actually on the antenna. Yeah, the third one is actually on advanced multiple access. So we are talking about NOMA. If you heard about NOMA, non-orthogonal frequency division multiplexing. Yeah, and they are also talking about modulation. Yeah, future modulation encoding. All right. So this is actually the area that currently what do you call that, cover within our group. Yeah, maybe not by us, but by some of our colleagues as well. Yeah. So because my area is actually on antenna, and I think Prof Yuli also from antenna, so basically it will be good for me to what do you call that, focus more on the antenna. So basically today we are going to I'm going to explain about some of the research activities that has been conducted by some of our students, yeah, in UTM, right? So when we are talking about mobile communication just now, we are talking about speed. Yeah, 1 gigabit per second, 10 gigabit per second, 100 gigabit per second. Yeah, so we're talking about higher speed. Yeah, so that will be what do you call that? Will be faster. Yeah, for us to download. Yeah, and to do a lot of our what do you call that, activities. Yeah. So how can we improve this capacity? Yeah. So according to Shannon law, yeah, the capacity itself is actually equal to N times W times log 2, yeah, 1 plus signal to noise ratio. So basically, from this equation, if they say we can improve the N, which is number of antennas, or we can improve, yeah, in terms of spectrum, that we usage of spectrum, or we can improve the signal to noise ratio, basically we will be able to improve the capacity. Yeah, so basically I will show you on how each of these what do you call that points, can be used, to increase the capacity. All right, so as we know, right, from frequency from 700 megahertz up until 2.6 gigahertz, yeah. So the current frequency, at this lower frequency band, basically the most bandwidth that we are able to use is only up to 200 megahertz, which is very small. But if they say we move to higher frequency, for example, at 28 gigahertz, we can see that, they have like 1.3 gigahertz of bandwidth which is still available. Yeah. But if they say we go much more further for 28 and 38 gigahertz band, so they actually like 3 gigahertz of bandwidth which is still available. Yeah. And if they say we go much more here, so of course, we'll have, for example, at 60 gigahertz, and we have like 7 gigahertz of availability of the bandwidth. So meaning, if they say we go to much more higher frequency, then we have abundant of bandwidth that we can use. So that's why for the 5G, we are talking about mid-range, high range, as well as the low range of the 5G spectrum, which can be utilized, because of this, but the problem is actually whenever we increase the frequency, because according to equation F equal to 1 over lambda, whenever we increase the frequency, the lambda wavelength will be smaller. So whenever wavelength is smaller, then there will be an issue, especially those who are actually living in tropical region like us, like me, like ibu-ibu dan bapa-bapa semua, di Indonesia, we're actually living in tropical region. So the intensity of rain rate, or we call it as a rain tension, is actually very, very, very high. So from this figure, it shows that, at 28 gigahertz, which is at mid-range of the 5G, right? We can see that at 110 millimeter per hour rain intensity, the rain intention is equal to 4 dB at 200 meters. So let's say we are talking about 1 kilometer, and we can see that the rain intention will be 5 times higher, which I would say is very, 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 very huge. So this is actually an issue. If they say we use frequency at higher frequency. So how to solve it? So one of the way to solve the issue is actually by increase the gain. So how to increase the gain? Basically, we can use array antenna. So basically, I think Prof Yuli also have done a lot of array antenna. I think in the first pictures, which it shows about the array of antenna. So basically, from this figure, we can see that, at the same area, 60 times 60 millimeter, this is at 3 gigahertz and this is at 30 gigahertz. So basically, at the same area, but at different frequency, we will be able to have like many more elements. For example, this one only one element, but here we have like 64 of elements. So basically with that, then I think we should be able to improve the gain of the antenna, and subsequently improve the overall system of the communications. But of course, when we are talking about array, then there will be a lot of issue, which is one of the things about mutual coupling. So I think in one of the in the machine ground itself, I think we are talking about how can we use metamaterial in order to improve in terms of the solutions, and cater for the mutual coupling effect. And the third one is actually on the second one is on the number of antennas. So basically, when we are talking about number of antennas, of course, nowadays we are talking about base station with a lot of antennas, and then there will be a lot of functions. One of the things is actually for the beamforming, maybe we are able to simultaneously communicate, with the base stations, and eventually, I think currently the trending now is actually on the IRS, intelligent reflective surface, and if they say we read articles from Sharul, they have conducted some demonstration on this IRS. The third one is actually on the signal to noise ratio. So basically, in order to improve the signal to noise ratio, basically we call it as a beamforming network in order to do that. All right. And in terms of the beamforming network, we can divide it into two, switch beamforming or adaptive beamforming. Right? So basically by using this beamforming, we are able to direct our communications to the intended directions, and we can direct the nulls, so this is actually the nulls to the direction of the interference. And this is actually the adaptive beamforming. Basically, by using the adaptive beamforming, we are able to enhance the directivity, as well as minimize the interference. And I think we can use it by using a lot of we can use in terms of algorithm. So currently, we have a lot of algorithm that can be used, in order to do this adaptive beamforming. And this is an illustration on how we can increase the directivity. So from here we can see that, by reducing the side lobe, the side lobes, we are able to reduce in terms of the interference, from the back loop, and obviously, we can improve in terms of the directivity. And the second one is actually in terms of the switch beamforming. Basically, switch beamforming is where we can switch from the predefined beam. For example, in this case, we are talking about this beam. So basically, we should be able to switch the beam from one beam to another. So in terms of techniques, there are actually many techniques that can be used in order to come up with this switch beamforming. For example, like Roman lens, blast matrix, Nolan matrix, Roos lens, and Bartle matrix. So basically, in my research in UTM, basically one of the works that I've been working on is actually on the Bartle matrix itself. Why I choose Bartle matrix? The reason is because it is simple and easy to fabricate. It requires only a few microwave components. For example, in this case, we are talking about the coupler. So we have like, this is a 4x4 Bartle matrix, and we're talking about 4 couplers. To this is 45 phase shifter, this is 0 degree phase shifter, and this is actually, we call it as a crossover. Crossover is actually a cascaded of the coupler itself. And basically by using this Bartle matrix, we are able to generate narrow beam, high directivity, and orthogonals. So this is actually why we choose to use Bartle matrix. So this is actually an illustration of the coupler. So we have the coupler. This is 45 degree phase shifter. This is the crossover, and this is actually the 0 degree phase shifter. All right. So in order for us to understand more about the beamforming, basically it will be good if they say we can understand about the array factor. So this is actually an equation for the array factor. So basically from this equation we can see that if they say we know the displacement of element, D, and we know number of radiating element, how many radiating element that we have, and we also know the phase excitations, beta. So we will be able to generate a beam angle. So as you know, when we are studying about antenna, basically in order for us to change the beam, we can either change amplitude or we change the phase. So basically in this technique, basically we use to change the phase instead of change the amplitude. Meaning we remain the amplitude to be consistent, but we change in terms of the phase itself. So this is actually an illustrations of 4x4 Bartle matrix. So in this case we have 4 input port and 4 output port. For example, let's say we assign one of the input port. Let's say we're talking about input port number 1 here. We assign it. So basically at output number 5, output port number 5, we can have a phase of minus 45. And let's say we assign input port 1 and we see the output at port number 6, we can see that we can create minus 90 degree. Output port 7 minus 135, output port 8 is minus 180. So from here we can see that the phase differences between each of the output port is about minus 45 degrees. So the same thing goes if let's say we assign input port number 2, 3, and 4. Basically it creates phase differences of at different degree. So with that, then I think we are able to create a beam at different of directions. Okay, for example, in this case, we are talking about plus 12 degrees, minus 12 degrees, plus 50 degrees, as well as minus 50 degrees. Yeah. Okay, so this is actually an illustration of beamforming network. Yeah, this is the beamforming network integrated with this array antenna, and then we are able to create different beam. Yeah, when we assign a different input port from here. Okay. Okay, so basically I had shared with you about the conventional bathymetrics. Okay, so now I also would like to explain about what we have done in terms of the multi-layer bathymetrics, where with this multi-layer bathymetrics, basically we are able to enhance the bandwidth as well as reduce the size by by omitting the crossover over here. So this is actually how the bathymetric looks like when they are actually multi-layer. Yeah. So from here you can see that this is actually the coupler. Yeah. Of course the shape it looks a bit different, and this is actually the phase shifter. Yeah. And basically from here we can see that we have the lower layer as well as the top layer. So basically the signal from the bottom, they actually couple to the top layer by through the slot. Yeah, basically in between the top and the bottom layer we have a slot. So this is where it can be coupled together. Yeah. So in addition to that, we also have done we call it as a transparent and flexible antenna. Yeah. Why we have to do the transparent and flexible antenna? Because I think we can see that there's some kind of application and requirement. For example, currently in Malaysia, if they say we travel through the highway, toll, currently they are using RFID, where the RFID itself is actually attached to the lamp of our car. Yeah, so basically this is where we have to make sure the antenna itself is actually not something which is transparent. Yeah, the same thing. Let's say you travel to Jakarta Central, you can see a lot of the things are glass building. So if they say we have antenna which is which is not transparent, then it looks very weird. So that's why this is actually a requirement for the transparent antenna. So basically for this transparent and flexible antenna, basically we have done some works on that. So the first one actually we have designed the CPW transparent antenna, designed on AGHT 8 transparent thin film. Yeah. So basically in this antenna, basically we use staircase techniques as well as rectangle stub in order to increase the bandwidth. Yeah. So from here you can see the bandwidth is covered from 3.15 until 32 gigahertz, which is very wide. Yeah. Which is ultra wideband. Yeah. And we also have designed CPW, CSRR, complementary split resonator UWB transparent antenna. Yeah. So basically this is actually how the antenna looks like. Yeah. And over here we have the CSRR, the complementary split resonator. So the function of this CSRR is actually to create a notch. And because as you know, for UWB it covers from 3 to 10.6. At around 5.8, yeah, they are actually they call it as an ISM band. Yeah. So in order okay, all right. So in order to this one, I think we create the notch. Yeah. Okay, so I think I just go to the time. Yeah. So I think this is actually some antenna that we have collaborated with University in France. Yeah. We call it as a transparent and we call it as a conductive. Composite antenna as well as antenna which use PDMS as a substrate. Okay. Okay, maybe I can just go through. Okay. All right. So this is actually the printing technology. We also have created some antenna by using the printer. Yeah. But we also have characterized multi-layer. Yeah. Because we found out that if they say the layer is only one, the resistivity is actually very high. But if they say we increase the layer, then it will be in terms of resistivity is actually much more lower. We can improve in terms of the resistivity. Okay, I think some of the case study. So this is actually some of the works that we have been collaborated with industry as well as a grant that we received from Japan. Yeah. So the grant, call it as EVO grant, Asian EVO grant. Yeah. So this is the project where we use Bluetooth in order to communicate or in order to identify the ETA for the users. Yeah. So basically from here you can see that we install ST mode on the bus, and over here we have the Raspberry Pi. Yeah. Then whenever the bus pass through the bus stop, yeah. So basically, it will be able to detect the bus, and the signal will send to the cloud, and from there, then we can do deep learning, and then from there, we will be able to send the information to the users to know the ETA. Yeah. So this project, I think, consists of 6 different universities. Yeah. Yeah. So we hope that in the future we can also collaborate together. Yeah. For this grant. Yeah. Inshallah. Okay. All right. So this is actually a testbed in Johor. Yeah. Right, so the distance about 20 kilometers and 30 kilometers away in Johor, and this is actually the test bed where we have in Malang, yeah, which is in Jawa Timur, yeah. So but over there they use only for school bus, yeah, right. Okay, so this is actually how the beacon looks like. It's very small, yeah. Okay, so meaning in order to use this, it costs cheaper price compared to conventional GPS as well as the router. Yeah. All right. So this is actually some of the project that we have been collaborated with Johor State government. Yeah. All right. Okay. So basically from here we can see the antenna play a very important roles, yeah, in the communications. We need antenna. Yeah. Whatever applications that we use, yeah, in mobile, we still need an antenna. Yeah. Okay, so basically from here we can conclude that designing antenna with beamforming capability will be able to support for the future wireless applications. Yeah. Okay, so acknowledgement to our collaborators. Yeah. So thank you. Okay, Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. Terima kasih. Sorry.
Thank you very much. Let's give a big applause to Professor Sharul Kamal. Okay. So now we go to the second. Oh, I'm also now talking in English. You influenced me to talk in English. Okay. So the next speaker is Dr. Norhudah Seman. So I will read a little short biography. So she received her Bachelor of Engineering in Electrical Telecommunications from Universiti Teknologi Malaysia in 2003. And then her master in radio frequency and microwave communications from the University of Queensland, Australia in 2005. Then she obtained her PhD degree in electrical engineering from the University of Queensland in 2010. So she studied the bachelor, yeah, in UTM, while Professor Kamal master, yes, a little bit different. So she was working in industry, yeah, before she entered UTM. So she was an engineer at Motorola Technology Penang, where she was involved with the RF and microwave components design and testing. She was director from July 2018 to 2021, and acting director from July 2021 to June 2022 at School of Electrical Engineering, Faculty of Engineering, UTM. Oh, okay. So recently then, yeah. So currently she is Associate Professor in Faculty of Electrical Engineering and also the Director of WCC, yeah. So her research interests concern the design of microwave, millimetre-wave devices, the effect of electromagnetic field radiation, including specific absorption rate, SAR, yeah, and power density and wireless communications. So this is a short, brief CV, yeah. Please, Professor Huda, come to the stage. So around maybe 40 minutes. I think we still have time before Jumat prayer, yeah.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi. Okay, so apa yang saya ingin sampaikan pagi ini adalah susulan daripada antena yang disebut dari semalam dan juga disambung oleh Prof Sharul. Siapa yang tak ada mobile phone di sini? Anyone that's not using mobile phones? So Anyone using smartwatch? Okay, definitely, right? So that's why it's been mentioned by Prof. Sharul that most of us, I think that using around probably at least one or probably up to 4 or 5 wireless devices. Lepas tu kita pun ada base station kan. So semua tu ada antena. So when we have antenna, we're going to have radiation. So tajuk di sini adalah melibatkan radiation daripada antena. Okay. So I will cover on the sub-6 gigahertz. Okay. Sebelum ni bila kita buat assessment dia melibatkan frekuensi di bawah 10. Tapi bila 5G come out in 2020, the standards, the guideline has been revised. So kita ada sub-6 gigahertz dan juga frekuensi di atas sub-6. Okay, itu. So hari ni saya cuba sampaikan sub-6 gigahertz dan juga Millimetre-Wave Electromagnetic Field Exposure Assessments. Okay, so this is the outlines of my slide sharing. So I will start with a little bit on the slide introductions to the 5G and how the involvements of the wireless communication related to these requirements of assessment, kan? Kemudian kita pergi tengok the parameter, okay? There will be some mathematics, okay? So we have a specific absorption rates and also power density, okay? And then we're going to actually learn a little bit on the exposure limits, okay? Then I will show on the SAS simulations and measurements, okay? So I will show a little bit on the SA that related to the single antenna elements. Then I chose the one that related to antenna array and also the assessment related to the power density. And then I will conclude the presentations. Okay, so this is actually been shown a lot, also been actually presented by Prof. Sharul. So we have the evolutions of wireless communications every 10 years. Okay, so we have a lots of demands. So in the 4G and 5G, okay, so especially in 5G, we actually require to use a lots of antennas. Okay, so we have to implement array, okay, in the base stations, also in the devices. And we have a lots of devices around us, wireless devices. So with that, we need to actually assess the radiations coming from this antenna, okay? So and then, okay, so this is actually also not new to us. We've been actually see this got a lot, okay? So 5G. So 5G is not only actually related to the mobile broadband, enhancements of the mobile broadband, but also actually concerning on the massive Internet of Things. So the devices connected. So we have a lot of sensors. So how it's connected? It's connected wirelessly, right? So we need antenna to add all these devices. Okay. So and then we have missions critical controls. Okay, so this actually to actually fulfill the demands of actually to provide ultra low, some for example ultra low energy, okay, ultra low complexity, okay, and then we have the extreme data rates, okay, very low latency, okay. So this is the demands, okay, this been actually promised by the 5G. Okay, so it's quite similar when we talk about the communications and when we actually talk about the 5G, even the future technology 6G. when we actually concerns in increasing the capacity. So there's three ways, okay. So we need to actually since at sub-6 gigahertz, okay, the frequency, the spectrum congested. So that's why it's quite early research by Professor Rappaport, which actually proposed 28 gigahertz and 30 gigahertz as the potentials, okay, quite a number of years ago to be actually a candidate for the 5G. So we actually exploring to have to use a higher frequency, since we have the congestions at sub-6 gigahertz, okay. So to improve the capacity, one's frequency, and then we need to have more antenna, okay. So with that, actually increasing the concerns on the radiations exposure from the base station, from the devices, okay. Okay, so in terms of the beamforming also, we have different actually types of radiations beam from the base stations. So in 4G we have sectorized, okay, beam, quite wide, but for the 5G we have beamforming, okay, a narrow beam dedicated to the user, okay. So we have, so the narrower beam, so it's mean that it has high gain. So is there anything that will a change in terms of the radiation effect to the user with this change of the characteristics of the radiation patterns, okay. So we're going to take a look in terms of that. So when we assessing the radiations, okay, exposure from the base station, from the device, so kita gunakan, we need to actually take a look in terms of the field regions. Sebab the radiation coming from the antenna daripada device ni, so kita kena tengok the range of this field. So yang first kita tengok near field, okay. So this near field, okay, it's located close to the antenna, to the device, okay. So in the range of R1, so R1 is equal to 0.62 square root of D cube over lambda, okay. And then we have actually a region between these near field, reactive near field regions, and also the the far field region. So it's between R1 and R2, which actually called as radiating near fields or Fresnel regions, okay. Then any regions greater than R2 is far field, okay. So let's take a look what is the parameter or how we going to assess these radiations at different regions of field. So kalau yang dekat dengan kita, so any device yang dekat dengan kita, okay, so contohnya laptop, okay, semua device kan, kamera pun ada connected to Wi-Fi, right? So dia ada antenna. Smartwatch, okay. So airport, so we have lots of devices, okay, quite close to us. We have Wi-Fi at home, okay. So anything that close to the humans, okay, to the user, we need to assess using specific absorption rate. So bila kita buat assessment, kita kena melibatkan badan manusia. So we use phantom, okay, to actually represent the human body. Okay. Satu lagi, okay, at the far field region. So at the far field region, we actually assess using power density. Okay. Okay. So itu quite actually clear. However, when 5G coming, okay, when we actually have 28 gigahertz, 30 gigahertz, 26, 40 gigahertz operating frequency. So when we calculate the lambda, even though the device close to the human body, it's already in the fluffy regions. Okay, so we need to assess using power density, but we need to include the characteristics of human body. So we have another parameter. So power density will be actually divided into two. One, incident power density without the effects from the human body, and another one is absorbed power density, which we need to include human body characteristics in the assessment. Okay, okay. So this is specific absorption rates. Okay, so it's actually a parameter that's actually measure or quantify the energy or from the radiation being absorbed to our body. Okay, so the unit is in watt per kilo. Okay, so when we see the parameter, these are actually related to the, okay, so this is sigma. So sigma is the conductivity of our human body. Okay, okay. Then this sigma is actually frequency dependent. We change the frequency, the conductivity change. Okay, and then we have this E, electrical field strength. Okay, and then we have this, okay, rho is to represent the mass density of tissue. So you need in kilo, okay, per meter square, meter cube. Okay, okay. So when we assess is actually in a volume, so it can be assessed using 1 gram or 10 gram of tissue. Okay, okay, okay. So then this is incident power density. So I've been mentioned. So the incident power density related when we have a source quite far from us. Contohnya from the base station. So nanti bila yang jauh tu kena check lah kalau kita nak buat compliant testing. So we need to perform measurements. So kita tengok what is the radiations. Okay. So ini melibatkan radiation source is quite far from us. So what actually influence this exposure effect? Okay, dia boleh jadi daripada segi the environment. Okay, kalau contoh kita ada blockage, tak blockage, ada bangunan, tak bangunan, is it the radiations like directly to us or not? So that will be actually influence the readings. Okay, dan juga antena parameter. Okay, so with the changes, previously kita guna sectorized antenna, okay, which actually cover probably dalam 120 degree untuk satu sector, and nowadays we have beamforming. Okay, so how it will affect? So definitely it will affect the incident power density. Okay, dan juga berapa banyak kita ada base station dalam satu kawasan, that will also affect, okay, the reading, the assessments. Okay, so kalau kita gunakan Millimetre-Wave, definitely the actually is very highly susceptible to the blockage. Kalau ada blockage je, it will drop. Okay, tapi kalau dia tak ada blockage, adakah we going to have more exposure? Adakah dia punya reading tu akan naik? So that's the things that we need to see. There's a lot of study that needs to be done related to that. Okay. Okay. So in terms of mathematical, so this coming from what we study. Okay. So when we related to the Millimetre-Wave, banyak benda yang kita tak boleh perform secara measurements. Okay. So we did mathematical study that related to the exposure. So in terms of mathematical, ini tak semestinya guna untuk millimeter wave, tapi it can be actually used at mana-mana frekuensi. Okay, so kat sini the power density, okay, is related to the, okay, this is transmitted power. Okay, then we have the antenna gains, okay, and also the number of the base station. So kita kena kira lah. Kalau matematik kita kira, kalau measurement kita letak je, okay, and then kita reading daripada spectrum analyzer berapa bacaan dia. Tapi kalau mathematical, so we need to know berapa banyak. Tapi we also, when we actually place the device to read, so we need to understand berapa banyak around us the base stations yang actually serve at that particular locations. Okay, okay, so it also actually related to this path loss. Okay, the path loss is given this one here. Okay, okay, so it's related to Z. Z is the locations kat mana actually we desired to perform the measurements or the assessments. And then we have X naught. X naught is the locations of the base station. Okay, so we have this power of alpha. So power of alpha is path loss exponents. Okay, okay. So the obstacle, selalunya bila we have anything obstacle, so we actually need to change this alpha. If you actually do the mathematical, so alpha need to change accordingly, so based on the environments. Okay, okay, so this is absorbed power density. Okay, so ini when we actually need to access any devices that close to human, yang kita guna dekat dengan badan kita. Okay, so SAR is being used for frequency below 6 GHz. Absorbed power density is being used for devices when we actually perform the assessment for the wireless devices that close to the humans with frequency greater than 6 GHz. Okay, so it's also sama seperti SAR, is actually will be dependent on the dielectric properties of human body. Cuma differentnya, lagi tinggi frekuensi, the wavelength shorter. Wavelength pendek kan? And then the penetration depth, dia tak boleh pergi jauh. So at millimeter wave, okay, the effects, we only see the effects at skin. Tapi kalau frekuensi rendah lagi, dia boleh penetrate lagi dalam lah tisu. Tapi kalau dekat millimeter wave, biasanya it will actually hit, maksudnya dia ada kesan lah pada kulit saja, skin layer. Okay, okay. So this is the equations. Okay, so it's actually related to the electric fields and magnetic fields, which actually this electric field and magnetic field will change when it's actually the signal penetrating the body. Okay, masuk skin layer, masuk dekat fat, masuk dekat masa, so it will change. Okay, so itu yang kita tengok lah when we actually assess the absorbed power density. Okay, so this is actually to shows how the signal been actually related or dependence on the dielectric conductivities of the human body. Okay, so this is the limits. Okay, so when we actually perform the assessments or the study, so we need to go through the guidelines. Okay, so this is the newest guidelines after 5G has been standardized. So there's a changes in terms of the frequency. Okay, some updates on the limit. So these actually basic restrictions, or we call as the guidelines, the limits guidelines. Okay, that related to, okay, So you see that, so there's a frequency, different frequency. Okay, so we have occupationals and general public. Occupational is someone that work, okay, probably with the close to the base stations, the workers. Okay, kalau general public kita lah yang gunakan. So there's a different limits. Okay, kalau kita tengok contoh di sini, okay, so sehingga 6 GHz, okay, so we have whole body average SAR. So kalau nak perform yang this part, kita kena buat radiation tu 30 minit. Okay, then kita kena buat averaging 30 minit, baru kita buat averaging. Kalau yang lain ni, yang 3 ni, kita buat 6 minit je. So we just do 6 minit and we do the averaging. Okay, so the standard different ikut frekuensi. Okay, so kalau yang ni sampai 6 GHz 0.4. So kalau dekat head torso SAR need to be less. Okay, ni limit maksudnya paling tinggi lah yang dibenarkan, 10 watt per kilo. So local limb, okay, 20 watt per kilo. So dia tak ada dekat sini. Okay, sebab dia this is SAB is absorb power density. So dia tak ada lah. So dia ada pada frekuensi atas 6 GHz. Okay, so tengok sini, pada frekuensi greater than 6, okay, GHz, for the whole body ada limit dia. Tapi untuk localize ni maksudnya dia at certain location. So kalau kita tengok kepala ke, so it's not averaging the whole body, dia specific location kat mana. Okay, and then kalau yang ada adalah this absorb power density, the limit. Okay, and absorb power density when we assess dia dalam bentuk area. So kena assessment dia, kalau SAR, the assessment averaging contohnya satu yang ni whole body, yang dua ni we average in 1 gram or 10 gram of tissue. But for this, okay, absorb power density, when we perform the averaging, it based on the area. Kita ni tengok juga frekuensi So kalau frekuensi bawah 30 GHz, we actually perform with an area with size of 4 cm². So kalau yang atas 30 GHz, what we need to use is 1 cm². So we need to actually, okay, do averagings based on that size. And when we actually expose the phantoms or the human body. Okay, so kalau kita tengok kat sini, so difference. So untuk limit bagi pekerja, the limit higher. The untuk public, the limit would be lower. Okay, sebab kita tak nak lah maksudnya dia ada maksudnya penurunan yang banyak lah daripada, sebab workers ni dia tahu kalau tiba-tiba exposure tu tinggi, they been trained. Okay, so they know what they need to do, turn off base station ke, macam tu kan. So tapi public ni sebab kita mungkin most of us tak sedar pun we been actually exposed to the radiation. So sebab tu limit dia sangat jauh lebih rendah berbanding dengan occupational limits. Okay, so this is okay. So this is related to, okay, most of us actually what we concerns more on the incident power density. So this the averagings when we do for 30 minutes. Okay, okay, so sama, the limits actually frequency dependence. So berubah frekuensi, kita kena gunakan limit yang berbeza. Okay, so the incident power density when kita buat, mostly that's related to the base station. Okay, bila the radiation source tu jauh. Okay, so this one when we do the averagings for 6 minit je, letak 6 minit, okay, dapat semua ready, buat averaging over 6 minit yang tadi. Okay, 30 minutes. Okay, so we have lots of frequency. So since 2020, So we need to revise. So previously kalau kita dekat human body pun kita guna power density. Tapi since 2020 when the guideline come actually includes the changes of the standard related to 5G. So devices kalau lebih daripada 6 GHz we need to use absorb power density. And then kalau anything frequency below than 6 GHz kita guna specific absorption rate. Okay, so ni antara contoh. This is the simulations. So the simulations in our lab we use CST. So we need to purchase the Vox cell model to actually to study the SAR. Okay, this is examples. Okay, it's quite early when we I think that we did this at early stage of study back in a few years ago, and already the students graduated. Okay, so we actually placed the antenna, okay, close to the head phantom, and we actually varied the distance. Okay, so from here we see that when we actually increase the distance from the phantoms, the SAR reduce. Okay, the SAR reduce. Okay, however, when we compare SAR that average over 1 grams and SAR that average over 10 grams, SAR average over 1 gram higher than 10 gram. Okay, because the size of the tissue smaller, the concentrations higher. So that's why, so any readings for 1 gram will be higher than 10 gram. Okay. Okay, so this is the measurement setup. Okay, in our lab. So the labs is accredited, so we able to perform compliant testing. So this is the only lab, SAR labs that's capable to perform compliant testing to customer, so from industries or research. Okay, so we have been accredited. Okay, so this is the setups. Okay, so we have the controller, so the software to control. So we have robots. Okay, this is actually move automatically. Okay, so we have the devices. Okay, network emulator. So the network emulator will actually act as base stations. So when the device need to communicate, so it need to communicate whether it's operate 2G, Bluetooth. Okay, so we need to control that in the assessment, 5G, so on. Okay, so this is our setups. Okay, so when we perform SAR assessments, whether it's simulations or measurements, it need to be operated at the maximum frequency, maximum power, maximum allowable power. So for 2G, 3G, 5G, so that's a maximum power. So it needs to be operated at maximum power, so we can get the worst case scenario. So that the SAR for that device, so reported SAR. So if you check your device, actually there's a link or a report that stated what is the SAR value for the device. Okay, okay. So let's take a look on how SAR will be varies. Okay, this is coming from our literatures and studies. So we actually, after a few years conducting this research, we actually able to understand what the things will be actually affecting the SAR. Okay, so first of all, okay, when we actually perform the study and also when the customer coming to us, so we realize that, okay, the antenna, the types of antenna, okay, will actually give different effects of SAR, and also where the positions of the antenna in the device. Okay, So if the antenna in the device located quite far from, let's say this your headphones, okay, so if the antenna placed at the tops of the headphone, it means it closer to heads, okay, then compared to the another one that the antenna placed at the bottom, so there will be a gap, right, when at the bottom. So the antenna with positions at the top will give higher SAR compared to the one that placed at the bottoms of the device. Okay. So then, okay, that's one. Okay. So we also understand that when we increase the distance from the antenna, the SAR will be reduced. And then distance from the base stations and also the coverage. Is we further from the base stations, so there's a fact that we won't get good coverage. Kalau kita tak dapat good coverage from the base station, phone kita akan increasekan power automatically. When the phone increase the power, SAR will be increased. Sebab tu saya kata usually that we talk to the operator ataupun the public, it's not, kita bagus kalau kita dapat good coverage from the base station supaya our device transmit at minimum. Dia tak perlu transmit tinggi-tinggi, tapi kalau kita dapat actually the coverage dapat 1 bar, so the device need to transmit at its maximum. Tapi all the device, okay, has the adaptive, we call adaptive power control. So dia tak akan pergi lebih daripada the limit allow. So 2G, 3G semua ada limit. So okay, it won't actually go beyond that. So kita control lah supaya the user, the public safe bila gunakan devices. Okay, so kalau ada obstacles yang menghalang, okay, so we cannot get the good coverage from the base, memang device akan tinggi lah maksudnya. Dia akan transmit pada power yang tinggi. So power tinggi, SAR tinggi. Because it's related to the strength of electrical field. Itu kan. Kemudian jenis servis. Kalau kita guna untuk data, so it don't need to actually transmit at high power. SMS ke, WhatsApp ke, contohnya email. Tapi kalau buat voice call lagi tinggi. Power need to transmit at higher, okay, levels, okay. And then frequency. So frequency juga memainkan peranan. Okay, so nanti kita tengok yang lebih detail. Okay, okay. So yang ini, so we actually when we perform the study and also the literature review, we see that, okay, yang kita jelas, if we average at 1 gram, mesti lebih tinggi daripada 10 gram. Kalau sini saya tak sure. Kalau Malaysia memang ikut Europe, so kita guna ini. If you use FCC, American Standard, it will average at 1 gram. Cuma kalau lab kita akan buat dua-dua lah. Kita cakap dengan customer, you need to decide. Contohnya, which actually standard that you going to use. And also it depend pada country. Kalau Malaysia, sebab kita memang ikut Europe, so kita average at 10 gram. Selalunya yang kalau nak fail selalu, ni cepat fail lah. Kalau fail, kita kalau lab kita just return balik lah. Kalau dia bila return balik, mungkin the designer or the manufacturer need to take a look in term of design. Dia kena reduce the SAR sampailah boleh. Kalau dia tak reduce, dia tak boleh pasarkan, tak boleh market the device. Okay, so since, okay, so yang ni lagi, okay, so bila kita increase power, so when the device actually transmitted at higher power, so definitely the SAR increase. So ni memang jelas lah itu. So kita pergi tengok faktor seterusnya. So this is the designs of the antenna. So kita tengok juga kalau the design of the tanya, contohnya the ground increase, ground decrease, kalau kita increasekan ground in our design, gain akan increase, kan? So kita tengok what is the effects to the SAR. So this is, okay, this column we have increments of the ground, okay, gain increase, tapi kita tengok SAR decrease, kan? Tak semestinya maksudnya bila gain, kita cakap pasal gain tinggi, tapi kita tengok SAR dia decrease. So the trends sebenarnya kalau ikut antena lain. So we cannot say that it will behave similarly. That's why when you design, kalau nak masuk dalam device, okay, it need to be evaluated. Dia tak boleh kita assume this would be actually produce low SAR. Okay, based on, so there's a, no matter what, when we design, we need to actually assess the SAR. Okay, so a lot of study also shows that kalau kita guna patch actually produce lower SAR compared to dipole, compared to helical or PIFA. Cuma macam tu lah, when we study, saya dah berapa tahun ni, dia not necessary it would be providing similar trend. Okay, so ini adalah beberapa faktor untuk frekuensi juga. So generally what we actually use when the frequency increase, SAR increase, tapi bila kita study sebenarnya tak, it's not consistent. So banyak benda lah, kan, banyak benda yang tak konsisten. Jadi setiap device with the antenna memang kena buat SAR assessment. Okay, kita pergi seterusnya, antenna array. Yang ni menarik. Okay, the behavior SAR nanti dengan power density different. Okay, untuk SAR it's actually at near field. We actually, when we perform the study, when we have array, so kita check ni daripada 1 elemen, 2, 3 ke 4, okay, we actually see the reductions of SAR. So it mean that pada near field, when we spread the radiations area, sebab SAR ni dia based on concentrations of the E field tu. So bila kita reducekan tu pada near field, SAR will reduce. So that's why even though we excite with similar power untuk each of this antenna dengan single antenna, it will actually produce lower SAR. Okay, so this is very significant actually finding. So kita boleh kita tak adalah takut untuk implement array pada devices. Okay, sebab kita tahu the SAR will reduce. Okay, kalau tengok 4 ni dia paling rendah sekali compared to single element. Okay, so this is the summary. Okay, so yang paling penting tadi lah ni number of elements, yang lain tu agak similar. Okay, so ini power density, so the assessment. So this comparisons between the horn dengan a patch. So kita tengok the comparisons. Okay, so this is the power density. Okay, okay, this one. Okay, so when we compare, okay, patch with array of 2 by 2 and the horn, definitely lah horn ni dia akan produce higher power density. Tapi kalau kita tengok horn ni, yang ni early tadi kita increasekan distance from the radiation source, okay, dia akan turun. Okay, okay, so ini pula, okay, my postdoc study, so kita publish pada tahun 2021. So we try to take a look what is the effects kalau kita tambah base station, kalau kita tambah apa antena elemen. So kita tengok finding dia. Okay. So kita ada dua ni. Ini adalah untuk sub-6 GHz. Kita study pada 2 GHz masa ni. So yang ini millimetre-wave base stations. So yang ini kita study pada 28 GHz. So kita varied number of antenna element, kita varied base station. So the finding is, kita tengok first. The presented result shows that the IPD tu incident power density, coverage probability and the average IPD increase with the increment of base station. Which actually will increase the EMF exposure. Increase base station, increase lah power density. Lagi tengok kat sini. It's found that the millimeter wave contributes more EMF exposure to the user than sub-6 GHz tier due to the use of directional antenna. Tu ada efek sebab kita guna directional antenna. Kemudian, jelas sekali, increasing number of antenna elements at millimeter wave base station will lead to a stronger IPD. So kita kena limitkan. Number of base station, number of antenna. So that will conclude my sharing. So kita dah tengok on the assessments with the device close to us, dari base station. So kita daripada mula-mula kita study only ataupun the assessment tu, the standards and actually take looks in terms of SAR dengan power density, but when 5G coming, so we need to include absorb power density. Untuk absorb power density ni very baru, so there's not a lot of study been done. So untuk kita pun kita just started in these few years. Tak banyak result lagi lah. So I think that's all from me. Thank you so much.
Thank you very much. Let's give a big applause to Dr. Norhudah. Please, Professor Sharul Kamal, come to the stage. Bagi yang di chat, bagi yang di online, silakan chat kirim pertanyaannya sambil kita menunggu di chat room. Apakah ada pertanyaan di sini, di floor? Silakan angkat tangannya. Anybody has questions here? Not yet. So let's see from the Zoom. There is already a question from Mr. Yuyu Wahyu. He shared some pictures. Can you show the picture? Click the chat. Can you see, Professor? This is one picture. Can you show the next? TRM pada sistem radar. Block diagram from TRM. And then another picture is the block diagram transmit to receiver module. So now the question. In the active electronically scan array or AESA system, there is a transmit-receive module which can regulate phase and power. Usually 1 TRM is used for one antenna. How does AESA relate to smart antennas? Are they called smart antennas also? Please. Professor Yuyu, do you want to audio? Is it possible? This is Professor Yuyu, from BRIN. Do you want to speak? Can you turn on the mic? Can you? I think it's not possible. No, we can't hear you. Can you try to speak? Hello? Can you speak? Hello?
I think that I try to answer.
Okay,
So,
okay.
It's just that I'm not really familiar, okay, on the TRM, but it based on my actually experience or knowledge that related to when the array been actually fixed to the base stations, okay, for this one. So each of these antenna, they needs the radio unit, okay, so to fit. Okay, so for my understandings and also experience, so it can be serve one antenna or multiple antenna, because the most important in the this array, so the antenna need to have inputs of phase. So when we steer the beam towards different directions, so it need to be input with different phase. So we need some mechanism to actually controlling this input phase. Okay, so that's my actually opinions, or anything that can this one. So even though probably nowadays the TRM serve one antenna, but with our knowledge probably it can be used to serve more than one antenna. Okay, it's just that probably need some modifications to the configurations, to the structures. Okay, so that's all of these antenna, it need to have different phase. Okay, so that we can still, if we don't change the phase, definitely the beam cannot be still, cannot be changed the directions, because when we, it's not only steer this way, so we need also, that's because we when we install the 5G, we have problems with some communication. So sometimes the array horizontals, but we also need to think how to steer it vertically. So that's need to some of the lots of modifications or improvements in the system. It can be any system to fit the system. We actually controlling the magnetic phase to fit the antenna. Okay.
Okay.
I hope that I answered the questions.
We can't hear you, Mr. Yu. We can't hear you. Can you?
This ISA is the smart antenna or no?
Do you think it's the AESA? Is it? Do you think it is type of smart antenna? Category to smart antenna?
What is A stand for?
Active electronically scanned array that is using the TRM.
Yes, it's a smart antenna. Okay, so when we're able to steer the beam, okay, so it's become smart antenna. Yes, so it's scans when it have scanned array, so it means we can actually scan. We change the scannings of the beam. Yes.
Used in the KFX, the fighter aircraft in the Korea, yes, in Borneo, yes. So in the ISA radar, so we are developing with the ITS or the TRM, yeah. But this the new method for phase shifting in the software, yes, not in the hardware for the phase shifter. Okay, thank you.
Oh, actually, it can be implemented electronically or using the physical phase shifter. Okay, there's a lots of methods on actually to produce phase difference. So I think that because we more familiar on the wireless communications that related to the base stations, things on. I'm sorry that we're not actually not that familiar with the radar systems, but actually it's quite similar. So the concept, the basic concepts are very similar, and it can be used.
Okay, thank you, Mr. Yuyu. Okay, are there any more questions in the chat, Mr. Adit? Oh, not. Okay. So, how about again from the floor? Are there any questions? Ya, kita tiap hari ya terekspos ya dipapar oleh gelombang elektromagnetik. Nah, tadi ditampilkan ya. Nah, dari BTS, dari Bluetooth, dari Wi-Fi ya. Bagaimana nih efek ke tubuh kita? Kita belum tahu. Kita harus nunggu mungkin 100 tahun ya baru bisa tahu efeknya. Tadi dia sudah mencoba menampilkan dari SAR-nya ya. Nah, ada yang ingin bertanya lagi? Yang umum boleh, terkait UTM boleh juga. Ya. Oh, di chat ada lagi. Tapi di sini ada nggak? Belum ada. Baik. From the chat, there's another question, ya. From Prio. Can you make it bigger? Professor Norhudah. Oh, it's from Brin also. Yeah, Professor Norhudah said that research related to absorbed power density has not been done much. So, what are the research topics that need to do related to that? Please.
So previously when we did or other did related to the power density, even though it's closed, we use same methods as incident power density. It's just that when 2020 the guideline comes and we need to change, so we need to include the phantoms. So nowadays the researchers that conducting research related to this, so what we need to actually understand is to what is the effects, okay, when we have the first single antenna, so we increase the frequency, so what happens, okay, to the absorbed power density, and then what happen when we increase number of antenna that being close to us, so what happens, okay, and then we also needs to actually understand what we research now, okay, understands how the designs of the antenna will affect the absorbed power density. So different antenna behave differently, okay, so we need to understand how's the electric fields, magnetic fields, the surface currents from the antenna, okay, affects, and also just the because the body will absorb, so there will be electric field, magnetic fields, the current surface coming to us. So we also actually study what is the behavior of these electric fields, magnetic fields, and also the current density at the human body, okay. So that's the topics. So you can actually, there's a lot of a room you can actually take a look at SAR, because SAR we understand quite a lot after these 10 years. But as of power density, because most of us started around 2020 or maybe 2019, so not much study has been done. Okay, so there's a lot of room actually. We can actually go back to the SAR, so implement it using the same methods, but implement it. You take a look what happened, because it is the finding will be still unknown. I cannot answer that yet, because I already did it. I think probably in 2-3 years. Okay, but there's a lot of things that we need to learn. But from our master students, what we learned, the effects at millimetre-wave only happens at skin. It's not able to penetrate. I think that's
A little good news.
yes, a little bit knowledge that we able to find. So there's a lot of room to actually to study.
Okay. Have you found any related or maybe publications about information, the impact of all of this wireless communication around us that maybe can harm the human, the brain or something like that? Did you find any information yet?
Okay, so since we're actually doing a lot of activities related to electromagnetic exposure, so every year we need to report to WHO. Okay, so that's so we me myself actually one of the communities, national community in Malaysia, so we report every year the findings from our research or the services that we perform for the customer, the industry. Okay, so in terms of the long-term effect, is actually been currently been done. So we still waiting for the results actually. So our partner UPMs started to do that, because we actually electrical, so we cannot see what's actually going to happen probably to the cells. Okay, so we have a partner to do that, and there's a lot of universities outside actually doing that, but it needs to have a lot of data in many years to conclude something. But until now, WHO actually stated that, okay, even though it's carcinogens class 2B, maksudnya dia ada macam rokok dulu, dia tak tapi dia ada risiko itu macam mana pun. So that's why kita bila device tu, we need to ensure that it's mesti bawah. Kalau base station tu mesti comply. So jadinya dia ada, cuma tidak boleh dibuktikan. We cannot actually say, kita kan researcher kan, kita sampai ada data baru kita boleh kata ada effect. Tapi kita kena hati-hatilah, maksudnya kita kena make sure all the devices, all the base station comply. Macam tu. So itu yang kita buat lah as the engineers that work within this area, macam tu. Dan everything that kita report lah pada WHO. I believe that, so I think there's probably someone lah ataupun agensi yang bekerja seperti ini juga di Indonesia. Sebab information ni penting kepada WHO, macam tu kan.
Okay.
Salab lah macam kita, sebab kita ada salab lah untuk
Starlab. Like in Singapore they also have Starlab, yeah.
Singapore.
No, you don't know.
There is, but sometimes even the product coming from, we actually receive the product coming from Singapore. Okay, so we not only actually provide the service in Malaysia, but also in the region. So we also now partner with Motorola. So because SAR is very niche, there's not a lot of a lab, so we need to be partners. But kita, when we accredited, so we need to do comparisons, measurement, testing. So tak banyak, jadi we able to partner with Motorola currently.
Okay. Well, actually, we can have more discussion, but the time is limited. Yeah. So let's once again give a big applause to these two wonderful speakers. I would like to ask Dr. Arif Udiarto, he is our head of department, to come down. Yeah. We want to give thanks of appreciation for both of these speakers.